Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera to everyone. So today I'm going to give a lectures on the fourth topic on the soil mechanic course, which is water in soil. But this will be the first part, and for the first part also I will divide into two parts, which is the first part will cover on the some fundamental and also theoretical parts on the water in soil. We'll introduce to you what are the parameters that will be measured based on this topic. And for the second part, for the second part of the first part, I'm going to show you a video of laboratory testing and also some example. Some example. Okay, for this part, what you are supposed to know is, in the end of this topic, hopefully you will know how water flow in soil. You also will know how fast water flow in soil depends on different types of soil. Okay, and does water affect the soil conditions? Okay, if there's any permeations or if the water penetrate into the geotechnical structures, okay, will that affect? Okay, will that affect the soil condition and also to the structure itself? And why do we need to know water flow? Okay, so we are going to discuss the flow of water, okay, within the soil particles. Therefore, you have to know first what is actually a groundwater. So when you're talking about groundwater, you know that it is a ground means that you're talking about soil. Okay, water definitely is water. So you are talking about water in soil. Okay, you're talking about water in soil. So what is actually groundwater? Groundwater refers to all subsurface water. Okay, all subsurface water. And water beneath the surface of the earth, which saturates the pores and fractures of sand, gravel, and also rock formations. Okay, so not only for soil, it means that you're talking about ground, it can be also soil and rock. So we are talking actually about the water below your ground surface. So this is your ground surface. So you are looking on the water below your ground surface. So how actually water flow below your ground surface? So your ground will be either soil or rock. So how is actually the water can flow? Okay, as long as is there any pores. Okay, is there any pores? So let's say this is your particles of soil. So water definitely will flow through this particle. So it will flow through this, flow through the soil particles. Okay, and water may also occur close to the land surface as in wetland, or it also may lies many hundred of feet below the surface. So it's not necessary that water can be near to the ground surface. Let's say here, it can also, you may also sometimes, okay, discovered that water may be down 100 meter below the ground surface, okay, depending on certain situation. And the groundwater is stored in and moves slowly through moderately to highly permeable rocks called aquifer. So what is actually aquifer? Okay, you can read here. Okay, aquifer is a layer of gravel or sand, or maybe a layer of sandstone, cavernous limestone, okay, or even a large body of massive rocks such as fracture granite that has sizable cracks and fissures. Okay, so another thing that you need to know about groundwater, okay, comparing between groundwater and also surface water. Okay, groundwater is less susceptible to bacterial pollutions. Okay, that's the reason why we, in terms of drinking water, we prefer the groundwater because it's more clean. Due to what? Due to it has a less possibility for bacterial pollution compared to surface water. So what I mean by surface water is anything above your ground. So this is what we call as surface. Okay, if there's any water on top of ground surface, okay, which is exposed to the atmosphere, that is called as surface water. Here, anything below your ground surface, that is called as groundwater. So comparing between these two, okay, surface and groundwater, definitely the groundwater water from groundwater is much better. And the common dissolved mineral substances, the common minerals, for associated to groundwaters are like calcium, sodium, magnesium, potassium, chloride, bicarbonate, and also can also have sulfate. Okay. From an engineering mechanic point of view, groundwater in soil may be one of two types. One is, we call it as Vedus water, another one is phreatic water, also known as gravitational water. So it occurring in two distinct zones separated by the water table or phreatic zone. So this is your water table. If you look here, so this is your water table. Water table is the boundary between these two zones. So you have the first zone called is a Vedus zone, and the second one is phreatic zone. So anything lies on the Vedus zone known as Vedus water, and anything somewhere in phreatic zone, that what we call as phreatic water. So the separation between these two zones, is actually due to presence of water table. So anything above water table, this is what we call as Vedus zone, and anything below water table, this is what we call as phreatic zone. So what is Vedus water? It is found that in Vedus zone, which is unsaturated always. So in Vedus zone, normally also we call it as unsaturated zone. Unsaturated zone. And everywhere, as we shall see. So it is actually comes from the percolating water moving downwards to join phreatic water below the water table. So remember from the previous slide, we have a figure where, let's say this is, if this is your water table, so from here to here, this is what we call as Vedus zone, and from here to here, this is where your phreatic zone. Let's say we know that this is your Vedus zone. Vedus zone is above your water table, so definitely whatever above your water table, the parameters that will be used will be considered in geotechnical engineering, that would be either dry or partially saturated. Partially saturated. So let's say if you want to get the unit weight, or whatever parameters, the only parameters that may reflect to this zone is gamma dry or gamma saturated. Because of why? Because it is unsaturated area. But there's also certain cases where this area can be fully saturated. But just in certain cases, we will discuss that later. But most likely, in this area, it's either dry or partially saturated. Now it comes the capillary water. So capillary water held above the water table by surface tension forces with internal pore pressure less than atmosphere. So there are certain cases also, somewhere in your lies above your water table, that would be a capillary, known as capillary water. So this capillary water is also part of Vedus water. So if there's any presence of capillary water, so here, this area may be associated to fully saturated zone. So remember previously I said that for Vedus zone, it is normally unsaturated, so you use either dry or partially saturated. But there is a cases where if there's a capillary water, so this area up to a certain height, up to the capillary rise, this area will be wet. Will be wet. So if it's wet, there is a possibility also that area can be fully saturated. Vedus water is the water beneath the surface of the earth, which is located above the level of permanent groundwater. It is already discussed. And we also know that there are three distinct layers, within the Vedus water. So we have the upper layer, what we call it as soil, the intermediate zone, which may consist of subsoil and solid bedrock, and the bottom layer is water table. So water table itself is a part of the Vedus zone, and we also have the intermediate zone, and the last one is the uppermost layer, which is soil. Let's discuss about capillary fringe. Remember, capillary fringe is a component of the Vedus water. So the capillary fringe is the lower layer. okay, will lies on the lower layer. Because of why? The bottom layer is your water table. Water table is the lower or bottom parts of the vadose water, and the capillary fringe will only exist somewhere above your water table. So here is your capillary fringe. Okay, how actually these things happens? Okay, this thing happen if there's any cracks. If there's any crack somewhere on top of your groundwater table, so it will allow water from the bottom layer, which is, this is your phreatic zone, right? Below your water table is your phreatic zone. So it's allowed water from the phreatic zone to move upwards, okay, to occupy the cracks, and it will rise to a certain height, depends on the texture, or depend also on the most likely it will depends on the texture of the material, okay, material somewhere here, okay, in the area where the capillary fringe occurs. Alright, so the height to which water will rise above the water table is because of the sponge-like suction, depends on the texture of the material holding the water. Okay, when talking about texture, it means that you are reflecting on the type of soil. Okay, most likely if you have a fine grained soil, the water will rise much more higher, okay, compared to a coarse grained soil. Okay, because of why? Because fine grained soil, we have a possibility to holding more water as compared to coarse grained soil. So the water move much higher in fine grained material due to capillary force. Okay, how water can enter the ground and become vadose water? So this is the major sources of natural recharge, and this is the sources of the artificial recharge. Okay, we know that not all precipitation that reach the ground will penetrate to the vadose zone and become vadose water. Okay, this is due to what? Due to evaporation, sublimations, okay, and also may due to interception. Okay, where the tiny water droplet that evaporated will intercept with the rain. Okay, because if let's say the natural discharge is rain, okay, so due to heavy rain, okay, so this is your ground, okay, so water will penetrate into your ground surface, okay, but not all of them will remain here. Okay, some of them will be evaporate to the atmosphere back. Okay, so not necessary that all the water, okay, the recharge sources of the natural recharge will lies on the vadose water. Okay, so that's the reason why most likely at this area it will be either dry or partially saturated. Okay, water table, okay, it is also known as phreatic surface. Okay, above the water table is vadose water, and below the water table is phreatic water. So water table is the boundary, is the that separates between vadose and also phreatic zone. And the other some reference book denote it as phreatic phreatic surface. Okay, what is a phreatic water? Okay, we know that phreatic water greater than atmosphere pressure tends to flow laterally. Okay, it's a form cave passage by dissolving the limestone in all directions, as opposed to vadose action, whereby a stream running in a cave passage erodes a trench in the floor. And it's not usually, it's definitely been placed below water table, and it is a saturated zone which is consists of water and solid. Okay, this is your water table which separates your vadose and also phreatic. Okay, if you know that vadose is normally known as unsaturated zone, whereas for phreatic it will be theoretically saturated. So whatever parameters involved will be gamma saturated, or anything that related to fully saturated condition. And it's subjected to gravitational force, so it means that the flow of water definitely moving downwards, okay, follows the gravitational force. Okay, we have several forces related to soil and also water. One is gravitational, and then I move it to here first, and capillary. Okay, so what is a gravitational? Gravitational means that flow of water will move downward by gravity. Okay, ikut hukum alam. But if there's any capillary actions, okay, above the water table, okay, if there's any capillary actions, okay, water in normal condition it will moving downwards. Okay, but if there's any capillary action take place, okay, instead of water moving downwards, now water will move upwards. So in this situation is normally related to due to capillary forces. Okay, if the water moving downward, that will be due to gravitational forces. And what is adhesion and what is cohesion? Okay, we already discussed this one, okay, in previous topic. We know that you're talking about cohesion, you're talking about adhesion is actually the same thing. The ability of the material to stick together. Okay, ability of material to stick together. So it seems like a glue effect. But what's the difference between adhesion and cohesion? Okay, when you're talking about cohesion, you're talking about the attractions of the same material. Okay, water and water. Okay, same material. But you're talking about adhesion, you're talking about two different material. For example, like water and soil. Okay, but it is actually the philosophy is almost similar. Okay, the ability of the material to stick together. It's just that for adhesion, you're talking about two different material. In this case, you're talking about soil, okay, and water. But cohesion, you're talking about the same material. Okay. Water retention. Okay, what it means by water retention, it is actually the spaces that exist between soil particles, okay, called pores, provide for the passage or retention of moisture within the soil particle. Okay, or in other words, it is the soil ability to retain water, okay, which is actually strongly related to particle size. Water molecules hold more tightly to the fine particles of a clay soil than a coarser particle of a sandy soil. So generally, clay retain more water as compared to other types of material. So this is the ability of soil to hold the water, okay, to retain the water. Okay, we know that I also already discussed this one with you in previous topic. When you're talking about clay, okay, I'll give an example here is clay. So let's say this is your clay. Okay, I already mentioned to you that surrounding a clay, it has what we call it as double diffuse layer, also known as double water layer, where it has a certain charge of electron and proton. So this charge will attract another clay particle, for example, okay, to attach together. So it has the that special features. Okay, so and at this particular area also, okay, this area, okay, the one that double diffuse layer, okay, in this area, okay, it can hold more water. So if there's any attractions of water and water, okay, so it hold more water, so it's quite difficult for evaporations to take place. So if the water is there, it will trap there for a certain time. Okay, it's somehow like you have been locked in jail. Okay, you have a certain time to be released. All right. Okay, this figure shows you typical values of water retentions. Okay, when talking about water retention, you have another three parameters to be considered, which is field capacity, permanent wilting point, and available water. So what it means by these three parameters that relates to water retention. So all these three parameters is you are talking about the capability of those soil to retain, to hold water. Okay, so if you're talking about field capacity is actually the maximum amounts of water that a given soil can retain. Okay, that is the maximum. Okay, the maximum amounts of water that soil can retain. Okay, whereas if a soil too dry, okay, that plants cannot literate the remaining moisture from the soil particle, is said to be as wilting point. So too dry means that this is the minimum lah. Okay, in other words, it's a minimum amount of water that soil can retain. And the available water is that which the plants can utilize from the soil within the range of fill and wilting point. So this is the in between of maximum and minimum value there. That is what we call as available water. So this is the example of movement of moisture through soil particles for a different type of soil. If you look at here, it's really clear that a gravel can allow water to flow much more easier compared to sand, compared to seed, and finally clay. Okay, it is actually due to shape and also size of the soil itself. Okay. Why actually clay? Okay, you say that barely any space between particles for water to move through. Okay, it is because the shape of clay itself is plate-like. Okay, plate-like. So for water to flow, it has to go quite long path. Okay, as compared to if the particle is rounded to angular, so it's easier for water to flow through. Okay, this is the basic laws when you're talking about water flows in soil. We normally refers to Bernoulli's equation, where it's best explained by Bernoulli's equation. I'm not going to discuss this one quite detailed because I believe that most of you already learned this one in fluid mechanics, if I'm not mistaken, which actually is apply the same definition, the same concept. Okay, so when talking about Bernoulli's equation, we know that it is actually related associated to water flows through pipes. Okay, or any mediums, okay, that permit water to flow within that. And if you look at this Bernoulli's equations, okay, it explains the difference of level of water at two different datum, which affected also by velocity and also by height. So water will through soil if there exists a difference of height between 2 points. Okay, so to get the difference of height between 2 points, it means that you need to have a two different datum with different level. So that's the water can flow. It means that you have the gradient here. So this is actually the example also. Another laws associated to water flow is actually Darcy's law. Okay, it is states that the flow velocity is proportional to the hydraulic gradient. Okay, the velocity is proportional to the hydraulic gradients. Okay, with a given k value, the constant k value. Okay, so what is actually k? K is the flow constant, or also known as coefficients of permeability. So for geotechnical engineer, we are more familiar with this coefficients of permeability. So when you're talking about the flow of water at a certain time, which is a rate of water flow, okay, through a medium of porous medium, we denote it as k value. Okay, we referring to k value. The symbol is k, where we consider it as a permeability. So the permeability of soil is a measure of its capacity to allow the flow of water through pore spaces between solid particles. Okay, we already discussed this one. If you have solid particles, okay, and the presence of water, okay, we want to measure the ability of water to flow through from this point, let's say from this point to this point at a given time. So we're looking at the rate. Okay, that's the reason why the coefficient of permeability is expressed by velocity. Okay, millimeter per second square. Okay, or it can be also centimeter per year, centimeter per minute, or whatever, as long as you are measuring the magnitude and also the time. Okay. Okay, the larger soil void space, the greater will be its permeability. Okay, on the other way, the smaller the void, the lesser will be its permeability. So coarser soil, we have higher K value as compared to fine grained soil. Okay, it means that if you have a coarse grained soil, it's much easier for water to flow through that medium as compared to fine grained soil. Okay, here I listed to you several factors that are affecting the permeability value. Means that they affect the K value. Either the K value will be lower or K value can be higher. So one of that is the porosity of the soil. Definitely, okay, if the soil is porous, the K value will be higher. If the porosity or the void ratio is less, okay, the K value will be lower. This is normally talking about, let's say this is the loose sand, okay, and this is the dense sand. And it also affected the particle size distributions, okay, either well graded or poorly graded. Okay, the shape and the orientation of the soil particle, definitely, if you're talking about clay, even though it's a plate-like, okay, if it's been arranged like this, definitely it's quite difficult for water to flow through, okay. But if let's say it's been arranged like this, okay, so it's much easier for water to flow, okay, for a given similar shape of soil. And the degree of saturation also will affect the permeability, the type of cation also, and also the viscosity. Okay, it not only limited to these factors, it has more than this, but this is the most factors that will affect the permeability value. Okay, here are the typical values, the K values for a different type of soil. So you have a gravel, you have a sand with a mixture of gravel, and for a very fine sand and a clay or silty sand. So you have the range here, okay, range here for each of those criteria. And there's a remarks also here. Okay, if you look at here for fine grained soil, clay silt, it's normally remarked as practically impervious, which means that it's definitely what we're talking about, that it's really difficult for water to flow through that medium, okay, which normally we say that this is as impervious layer. Okay, we consider that theoretically, even though there is a possibility of water to flow through that area, but we consider that it is impervious. Okay, I think I will stop here first. Okay, we will proceed, or we continue with the first part of this topic later in the next video. Thank you very much.